Hello and welcome to this SlimDevOps episode. How many have we got now? 48. SlimDevOps episode 48. I'm Martin. If you're watching this after the fact on YouTube, this was originally streamed on twitch.tv/SlimDevOps. So if you want to head over to Twitch and give us a follow there, you can join these sessions interactively. Hello to those of you from the community that are returning. Good to see you all here again. Hello Big Pod, hello Eric. I see there's some others watching, silently lurking, but hello, welcome to the stream. Today I'm going to be going through a presentation that I prepared for the Comp42 SRE conference that I think I gave last week at that event, and I thought we can revisit it here. I can present the material but also go into some of the topics in a more practical way, and hopefully if you have questions, I can answer any specific questions that each of the topics will raise. Hello Lindsay, thank you very much for stopping by. Right, so I'm looking around at the various dashboards. Now, I am flying solo this evening. I see Big Pod is here. This is my colleague Primoz is here in chat. Primoz, please point out the inaccuracies when you spot them, and if you can help me stay on top of any questions that I might miss. It's a little bit harder. I've got quite a lot of stuff going on here in order to put this all together. So, hello, the dumbest idiot. Some of your usernames are fantastic. Hello there, welcome to the stream. So, let's flip over to here, where I've got the presentation lined up, and I'm going to be flipping between this and I've got a shell open somewhere, and Visual Studio Code will drop into some bits and pieces. But I thought I'd use these slides. I put lots of effort into preparing this. So some of this, if you went through the Container 101 series with Peter and I, which we did over about 12 weeks, sort of towards the back end of last year and the very beginning of this year, we're going to condense that down into a few slides and sort of touch on some of the best practice and why that sets you up for the best practices for the 5 security best practices. So let's start getting into this. So I will briefly introduce Slim.AI for anyone that hasn't been here before. Basically, we help you build secure containers faster. Slim.AI was created to give developers the power to build safer cloud-native applications with less friction. So that's the elevator pitch. And that's done with 2 components, our open source DockerSlim and also our Slim SaaS platform. And that allows developers to optimize their containers, reducing both the overall size and the vulnerability count. And we're going to be going into precisely those topics today in practical terms. And so by increasing the efficiency and decreasing the attack surface, Slim.AI ensures that you're only shipping into production what you absolutely require. So that's sort of the big pitch. You can go to the Slim.AI website to find out more about that. So here's the agenda for today. We're going to look at 5 best security practices for your production-ready containers. I've got an example app, so we'll take a quick look at that. Then we'll look at container best practice using several different techniques with a focus on where container best practice impacts security. And you should understand exactly what you're shipping into production. So I'll introduce several tools that you can start using today to help with that. Then we'll make an objective decision on what is the best base image for our example application. And finally, we'll minify the image with DockerSlim to significantly reduce the attack surface. So we're really going to cover it all. And I can rattle through this in half an hour. I'll go a bit slower today and give time for questions. If you have questions at any point, just type them into the chat. I will see them here and I'll respond to them, in each topic to try and keep all of that context together. So let's have a quick look at our example app. Here it is. It's a Python example. I think we've used it here in the past, but this was originally created for a CNCF webinar that we gave last year. So it's a very, very simple Python Flask application that implements an even simpler RESTful API. And the app is just for illustrative purposes. Its function is unimportant. We could have done this with Node or Ruby or any other, many other different languages, you know, some like front-end frameworks and what have you. This just sets out the stall, but we have implemented these examples with different language and framework ecosystems before now. So what we'll do is we're going to containerize this app using 4 different base images and differing container image composition techniques. So let's take a look at one of our Docker files. In fact, before we do that, let's see if I can get all of this to work. Let's do this. Here we go. Here's my code editor, and here is, as he clicks in the wrong place, here is my code editor, and this is the actual app that I'm, so you'll see, so I've removed some of the comments from the presentation and what have you. And the one in the presentation isn't Pepe compliant, but this one is. So there's our example app. So if we go back to the presentation, oh gosh, I need to click on these things. There we go. So let's look at a Docker file. So what I think we'll do is we'll go through this and then we'll look at one real example. So this Docker file, the one you're looking at right now, adheres to container best practice. It uses an official Python base image. It has a work directory defined for our application. It has good layer construction. So this minimizes cache invalidation and optimizes the build performance. Files are copied in only as required. Port is exposed, and it uses an entry point for proper signal handling. This is all stuff we've talked about here in the past. Here it is all collapsed down into one solid example. But there are a few things here that specifically help with container security. So let's just take a closer look at each of those. So the first is if you don't specify a user in your Docker file, your app will run as root. Nobody is an unprivileged system account that you will find is created by default and available for use in Debian, Ubuntu, Alpine, Distroless, and many other container base images. And the Nobody account is intended to run things that don't need any special permissions. So it's usually reserved for services so that if they get compromised, the would-be attacker has minimal access and can create limited impact to the rest of the system. By contrast, if your app is running as root, then the would-be attacker potentially has complete access to the container and possibly the tools and utilities that are shipped in the container that they can now use to disrupt your operations and infrastructure. So, least privilege always. What we do here is choosing a version number for the base image is often referred to as pinning. It's a slight misnomer, but it's often called pinning. And some tutorials teach newcomers to pin their images to the latest tag. However, containers are meant to be ephemeral, meaning that they can be created, destroyed, started, stopped, and reproduced with ease and reliability. And using the latest tag means that there isn't a single source of truth for your container's bill of materials, resulting in your container getting whatever the most recently updated version is. And a new revision to the latest tag, or a new container image revision, published under the latest tag, can introduce major version bumps of the system and the language ecosystem that you're using, which will likely introduce breaking changes. So if you pin a specific major or minor version in your Docker file, it is something of a trade-off. You're choosing to not automatically receive system upgrades and language improvements and fixes via the update mechanism. And it's an important distinction there between upgrades and updates. But most DevSecOps teams prefer to employ security scanning as a way to control the updates rather than dealing with the unpredictability that comes with the container build and runtime failures. So let's have a look. Eric has a question here. I just need to remember what I need to do. So Eric asks, I know that this is Eric, he goes by our podcast because he runs the our language podcast. So Eric asks, what is your opinion on Docker files that contain shell scripts for installing and configuring packages? Yes, that's fine, providing that you adhere to, awareness of the layer caching and all the rest of it. That can be a fine way to make your Docker file more readable, for example, by bundling up a whole bunch of complex operations into scripts that you call. I haven't done that here, but that can be done, and it can be done in a way that doesn't upset the build optimization or the security of your container. We will get to a topic later where, irrespective of whether you're using scripts or run commands, you need to be mindful of layer caching and how that may actually degrade the security of your container. So we'll get to that in just a moment. Good question though. Yes, so and Big Pod makes a point which we'll come to in just a moment. So let's move on to the next slide. So avoiding run apt-get upgrade in Docker files was considered best practice for a long time. But in the majority of cases, this really is not good advice. So base images from vendors and large projects are frequently updated using the same tag to include critical bug fixes and security updates. However, there can often be days go by between the updates being published by the distro vendor and the package in their package repositories and the revised base images being published to the registries. So relying on the base image alone is not sufficient, even from images that are blessed by Docker and maintained by companies with plenty of resources. So if you imagine a small open source project maintained by somebody in their spare time, that latency between images being republished with security updates can lengthen further still. So if you pin a stable base image, package updates are purely focused on security fixes and severe bug fixes, so you can safely apply system updates without fear of unexpected upgrades that may introduce breaking changes. I'm just looking at I think I will continue. There's some commentary, but I will come back to that at the appropriate moment. So always apply your updates is my advice here. And in this example here, what we're doing is we're applying these updates in a way that actually cleans up the cache behind ourselves as well to minimize cache invalidation or eradicate it entirely. Thank you for those of you that have followed us here, by the way. I think you can see in the chat there that we've just hit our 300 follower milestone, so thank you for that. So let's talk about layer caching. So Docker builds can be slow. So we use layer caching to reuse build steps from prior builds to speed up the current one. And while this does improve the build performance, there's a potential downside where the caching can lead to insecure images. For most Dockerfile commands, I'll bring up in fact, let's do it now. So for most Dockerfile commands, let's have a look here. Let's edit. Let's just look at the Python example, which is based on the Debian image. So most of these commands, these are all caps in front of the steps here. Most of those commands, it's the text of the command if it's the text that follows hasn't changed, so this bit here, if this hasn't changed, that determines whether or not the cache should be used, as opposed to the content. It's only when you use the copy command, that it's the actual content of the files that were copied that determine whether the cache is still valid or not. So in this case, all these apt-get, update, upgrade, install, run commands will add possibly old, insecure packages into your images, because this will continue to pull from the cache, the layer cache, unless this text changes. So when you're relying on those caching, you could pull in this old stuff. So sometimes what you're going to want to do is bypass the caching, and you can do that with a couple of arguments. So let's just flip back to our presentation here. Right then. So --pull always pulls the latest version of the base Docker image instead of using the locally cached one. And --no cache ensures that all additional layers in the Docker file get rebuilt from scratch instead of relying on the layer cache. So what this results in is, if you use those two arguments together, as is described here, the new image will always have the latest system level packages and security updates. So as a result, what you're probably going to want is the benefits of caching and security updates, and you want those within a reasonable amount of time. Then you're going to need two build processes. The normal image build process that runs whenever new code is released, and then a daily rebuild of your container images from scratch using --pull and --no cache to ensure you have all the security updates. So at that point, we now have a container image that adheres to best practice. Why did I do this? I've just tabbed away. Let me just do that. So let's take a look at some container scanning and analysis to understand what's inside your container. This is a topic that we've touched on quite a few times. I also see one of our community members, Takov, is here. Takov says, yeah, this is a trivial user error I have committed to many times. And I think there you're referring to forgetting that the layer cache may be stale and out of date, and therefore introducing an insecure set of packages into your image composition. So I'm not going to deep dive into the container vulnerability scanning or the generating of software bill of materials. That is something we've covered in detail here before. If you go to our YouTube channel, youtube.com/SlimDevOps, I think it's episode 46, we had Eric Smalling on from Snyk, and we took a deep dive into the Snyk security analyzer, and we've looked at software bill of materials generation and analysis several times in the past. So you can go and find videos that dive into that in more detail. So what I'm going to do is just say this: you should absolutely be performing vulnerability scans and generating SBOMs for your production containers as part of your image build pipelines, and you should be reviewing the results. And somewhere here, my colleague Primoz says you should get an SBOM every time you build anyway, if you ask me. So yes, we are aligned on that. You should be doing that absolutely always. For the purposes of this presentation, I used DockerScan, which is powered by Snyk, although you can use Snyk as a standalone tool as well. And I used Docker SBOM, which is powered by Sift, and something that we've used here in the past as well. Other scanners are available, including Trivy, Gripe, and Claire, and I recommend that you give them all a try. They're all excellent. the scanning and SBOM tools are extremely useful tools for helping to understand what's inside your container, and we'll look at some deeper level analysis in just a little bit. So, and here we are, in fact. So let's look at this very quickly. So I use the Slim.AI SaaS and more recently the Slim.AI Docker extension to sort of demystify containers and really get to understand what's inside them. And knowing what's inside your container is critical to securing your software supply chain. So the Slim platform lifts the veil on the container internals, so you can analyze, optimize, and compare changes before deploying your cloud native apps. So we could just take a quick look. Actually, I think I've got Docker here. I've got Docker Desktop here, and I've got our Slim.AI extension. The Slim SaaS platform and the Slim.AI Docker extension are both free to use. So let's just take a look at, oops, I clicked in the wrong window again. Let's try and do it the right way. So I'm going to look here. I'll look at the regular version. So let's just take a look at the overview. So this is one of the containers. As you can see, I've built my app inside several different containers, and they've been minified as well. We'll be looking at this a bit later, but here's the one from the Dockerfile we looked at earlier. We can see here that there's 9 layers. We can see what changes in each layer. We can choose a layer and see what was added and removed. We can even flatten the file view to make it easier to see. I think if we do that, we might get, yeah, there's a lot going on in that one. That was a big change. Let's look at something smaller. What was happening in here? Tree view. Okay, and then in the overview section here, we can see, here we go, we're using user nobody. We can see the architecture, we can see the base image. So although this is a container that's published by the Python project, it's an image that's based on Debian. We can see the port that's exposed, we can see how big it is, and then we can also see the shells that are inside, any special permissions on files and directories, certificate bundles, a whole bunch of stuff. But we can even compare different revisions of this container as well. And on the SaaS platform, you can do container optimization. You can connect all your registries, and all of that functionality is going to be exposed here in due course. So if you really want to get understanding what's inside your containers, you can do that here. And you can even see the reverse engineering of the Dockerfile to get a complete view of how that container was put together. It can be very useful in determining, sort of doing due diligence on your container images for your base images as to which are the quality containers that you want to use in your own infrastructure. Let me just bring this back up. So that was a quick look at the Docker extension, and we'll be having another look at that later because we'll actually be using it to do some vulnerability analysis. So what does this? Yeah, so choosing our base image. So we should try and start with the best security posture that we can. So the regular Python image, which we were just looking at our app inside, that was built from Debian 11. And it weighs in at 915 megabytes. In fact, I was using the Slim one. If you just get the regular image from Docker Hub, that's 915 megabytes before you even put an app inside it. But they do offer what they call their Slim versions, and they are smaller starting points. So I containerized my example application using 4 different base images, including the official Python image based on Alpine 3.15, the official Slim Python image based on Debian 11, a Distroless multi-stage build, and an Ubuntu 22.04 build, which doesn't include Python by default, so that actually has to be installed via a Dockerfile run command. So we can see here in terms of the base images, this is how they stack up in terms of size. And why is size important when we're talking about security? Well, the idea is that a smaller base image with fewer files, fewer packages inside it should have fewer vulnerabilities, and we'll test that hypothesis a little bit later. So I'm talking about fewer packages here, and sometimes it's necessary to install additional system packages, as I just explained, as dependencies to your application or to otherwise help the build process for your image. The Ubuntu base image that I'm using doesn't include Python, so that does need to be installed via apt-get in a Dockerfile run command. And there's a couple of examples here. But it's important to understand the default options for installing system packages with Debian and Ubuntu and RHEL and some of the other distros can result in much larger images than you need. That 915 Python official base image that I mentioned earlier is a good example. So more packages make the container image larger, which may in turn increase the attack surface of your containers and also impact the deployment velocity and the startup performance of the container. So when you do need to install system packages, avoid installing the recommended dependencies. So I've included some examples here for Ubuntu and RHEL that install Python 3 but without those unnecessary recommended packages, using --no install recommends in my Ubuntu base container. Reduces the image size by 266 megabytes. So what we'll do is we'll build our base images, build our app with each of those base images and see how the final image sizes stack up against one another. So here we are. We have got the results in terms of image size. So the images all include Python and our example application and our application's dependencies, our application's dependencies are 11 packages that were installed via pip. Pip is deterministic, so it's the same 11 packages in each of those containers now. And the adage goes smaller is safer. So a smaller image size should correspond to fewer packages, and that should result in fewer vulnerabilities. So let's check that hypothesis. And as we can see here, in terms of size, Alpine is the smallest, then our Distroless image comes in second, then our Slim image based on Debian from the Python project comes in third, and then a little bit behind is Ubuntu 2204. So the best idiot says slimmer is safer. Well, let's find out, shall we? Oops, I forgot to highlight the right screen. There we go. So there's no denying that the Alpine results here are excellent. The official Python image based on Debian 11 is not looking great, however. It's got 84 vulnerabilities in total, of which 13 are critical and 3 are high. And these are all in system packages installed via apt, so not any of the packages that were installed via pip. Distroless, which as it happens is also based on Debian 11, has 46 vulnerabilities, and of those 3 are critical and 7 are high. And again, these are all in system packages that are installed via apt. And with Distroless, it's also difficult to do much about this because unlike the traditional sort of Debian derived base images, there is no apt-get in order to install the latest updates. And that can be worked around, but it is non-trivial, so you're kind of stuck with whatever the base image provides you. And that brings us to Ubuntu, which was the largest container image by size, but has the second best vulnerability assessment. It has no critical or high vulnerabilities at all, with just 7 medium and 16 low risk vulnerabilities. And that begs the question, why is this? Ubuntu is derived from Debian, right? So, Ubuntu is a commercially backed Linux distro with a full-time security team, and Ubuntu has SLAs to mitigate vulnerabilities for their customers and their users, which also includes mitigating all critical and high vulnerabilities for the supported lifetime of the distro. Debian, on the other hand, is a community project, and while many Debian contributors, including myself, do fix security issues in Debian, it simply cannot provide the same level of commitment to security as the commercially backed Linux distro vendors such as Canonical, Red Hat and SUSE do. So, based on the information we have in front of us here, Alpine must be the clear winner for our application's base image. Unfortunately not. That is not the case. So why is that? Well, Python and Node and some other languages can result in significantly slower build times and introduce runtime bugs and unexpected behavior when running on top of Alpine. And this is due to the differences in muscle used in Alpine as opposed to glibc, which is used in most other distributions. And this topic in itself could be a talk in its own right, maybe one we can tackle in the future. So personally, I don't recommend using Alpine for Python apps, and I know there are people in the Node community that feel the same way, that they don't recommend Alpine for Node either. But Alpine can be great for Go and Rust, although you can still run into some friction with incompatible behavior or unexpected behaviors when using Alpine. So I see we've had some old friends join us. I know our podcast is keen for the stats. My stats are a bit limited. If you wanna hit me up on how I can make the stats more appealing, let me know. We could do something there. And hello, Yannick. Nice to see you again. Yes, perhaps Ubuntu is awesome. And my colleague Primosh says, it sounds like I've got that Ubuntu security advertisement memorized. Full disclosure, I used to work for Canonical. I was engineering director for Ubuntu. I know how things work there very well, and I'm aware that the commitment that the Ubuntu security team have to Ubuntu is comparable to what Red Hat and SUSE offer. But I'm making the distinction between those commercially backed distros versus the community maintained distros. So, what if I could have the low complexity of maintaining an Ubuntu based container and the security profile of Alpine? What if I could make my containers smaller than Alpine? Well, let's give that a try. So we're going to get into some container slimming now. So we can use DockerSlim or Slim.AI for that, and the terms slim, minify, optimize are used interchangeably here to describe the act of reducing the size of the container image. DockerSlim is our free and open source tool. It's available on GitHub. I think there's links rotating around over there that can tell you where to get that stuff. And both DockerSlim and the Slim.AI SaaS platform can automatically optimize your containers. So it doesn't change anything in your sort of container image process, but it can minify it by up to 30 times, making it more secure by reducing the attack surface of the container. So DockerSlim has been used with Node.js, Python, Ruby, Java, Golang, Rust, Elixir, R and PHP, running on Ubuntu, Debian, CentOS, Alpine and Distroless and many others. And if I've missed any, Primosh, let us know, because Primosh maintains a rather comprehensive suite of examples for different languages and frameworks and what have you. So at this point we always get asked how DockerSlim works, so I will briefly cover that. Although last week, so what would that be? Episode 47, so youtube.com/SlimDevOps, episode 47, Primotion I covered the most commonly asked questions we get about DockerSlim, and we gave a longer answer to how DockerSlim works in that talk, so I'm going to be very brief here. You can watch that for a sort of a deeper dive into DockerSlim. But DockerSlim optimizes containers by understanding how your application works and what it actually needs, using various analysis techniques, including static and dynamic tracing. DockerSlim will create a new single layer container image that only includes the assets from the original container that were required for your application to function. And you can understand how your container image was transformed before and after by using either the Slim SaaS platform or the Slim.AI Docker desktop extension to see exactly what happened in that transformation. And there are a number of benefits to slimming containers. So you should slim. I don't know what I've written here. I've got odd words in my notes. So you may be familiar with Kelsey Hightower's no code sort of parody GitHub project. So ship no code, deploy nowhere. This is sort of the aspiration of DockerSlim. Only ship to production what your app actually requires, and your Slim containers can be up to 30 times smaller. So Slim containers images are faster to deploy due to their lower size, and they're faster to start due to having fewer files inside them. And Slim container images can be less expensive to store and transfer. And Slim containers reduce your attack surface. So Aisha, one of my colleagues, prepared a report at the back end of last year called What We Discovered When Analysing the Top 100 Public Container Images. And that showed us that there's an increasing trend of dev, test, QA, infrastructure tooling being left in production containers. And unused shells and interpreters and tools and utilities left inside your container images can be used against your infrastructure to disrupt your operations if the container is compromised. So you want to make sure that that is always removed. So let's take a look at our slimmed containers. So we've slimmed all of the containers. So in most cases, there are significant size reductions to be had with slimming container images, regardless of the build techniques and base images used. In these examples here, we see between 3 and 6 time size reduction, which is quite modest by our standards, but still valuable all the same, as the container attack surface has been significantly reduced. In practice, we often see 10 to 30 times size reductions for complex applications. So our Slim Ubuntu based image is now just 5 megabytes larger than the Alpine image that has been slimmed. But with none of those compatibility concerns, because it's Ubuntu rather than Alpine and it's glibc rather than Muscle. And that Ubuntu container is now 37 megabytes smaller than the unoptimized Alpine image. So the question that remains is, has this slimming process actually improved the vulnerability assessment? So let's find out. I think this speaks for itself, but analyzing if vulnerable components exist in slimmed containers is currently a manual task, something that we're going to work on and make an automated capability. But it's a manual task for now, and the reason it's a manual task is that the metadata that the scanning tools use is often no longer available in the Slim containers. But that said, it only takes a few minutes at most to using the Slim.AI SaaS platform or the Slim.AI Docker extension to search for vulnerable components and confirm that they're no longer present. So we've already confirmed that the Ubuntu based image was free of critical and high risk vulnerabilities. So that's 7 remaining medium risk vulnerabilities, and those were in E2FS progs, which is Linux file system utilities, libsqlite 3, and Perl base. And it took literally seconds to confirm that none of those components exist in the slimmed image. So I'm going to actually demonstrate how I did that. So let's I'm going to need to look at one of the reports, I think, to do this, because I can't. Oh no, I can do libsql. Let's do libsql. So let's take out. I've clicked on the wrong virtual display again. Excuse me. Right then, let's take a look at our Ubuntu image that is not slimmed here. And we'll just get that analyzed. And what we're going to do is we're going to search for libsqlite. I think that will probably do. Here we go. There's a whole bunch of stuff we've found there. 7 objects in total. So some of this isn't, but here's the library here, and these are symlinks and what have you. So this is a vulnerable component. Now, if we go and look at our Slim container, so this is the same container, but the one that we've optimized with DockerSlim, and we do the same search. None of those files are present. Now, what that means is our application doesn't use libsqlite 3, so consequently none of those files and components exist in our optimized container image. So you might be thinking to yourself, well, okay, if your application doesn't use libsqlite, it doesn't really matter that that component was there or not, right? Well, it depends on the component. In this case, probably not, no. But imagine that it's a component that includes utilities, and those utilities could be, used in the shell. And if they're left behind, they could be used. It's the aggregation of the different vulnerabilities to be used together to create, an attack vector. So by removing everything you really don't need and the vulnerabilities that come with it, you make your container more secure and continues to be more secure the more of that vulnerability surface that gets removed. So that's just one of them, and you can see it just takes a moment to, when you've got your security report in front of you, your analysis report, it's very easy to see these are the affected components. Are these in the container, yes or no? We're going to do that again in just a moment for something that's a bit more relevant to our application. So I confirmed very quickly that the 7 medium risk vulnerabilities are all removed from our optimized Ubuntu container. So that leaves, and there were also, of the low risk vulnerabilities, 2 of them were actually with the Python mail cap module. So given that our application is a Python application, we're probably a bit more interested in this. And it was specifically in the find match function. So again, it took me just a few seconds using the Docker extension to confirm that the Python mail cap module was no longer present in the slimmed image. So let's head back over to the Docker extension and do this again. So we'll go back to our unoptimized container and we'll search for mail cap. And here we go. We can see, I've chosen the wrong option, haven't I? There we go. We can see here is the Python module. It's part of the Python itself. It's a pure Python module, and what we can see here is the compiled bytecode. So here is the mail cap module in the fat original image. So let's move back to our slimmed image. And again, we'll do the same search, looking for mail cap. And there's nothing here. So this is great. We're using Python. They may only be low risk vulnerabilities, but nevertheless, those components are simply not on the system. This is more pertinent when you're using an interpreted language, because if there are vulnerable components in modules of an interpreted language, you can manipulate those components from the interpreter if you've been able to compromise the shell. So this is compromise the container rather. So this is a better example of where, you know, removing an unnecessary component can have more substantive positive outlook on the security posture of your container. So let's, it's many windows right then. So it only took a couple more minutes using the extension to determine that the 6 remaining low risk vulnerabilities had also been completely removed from the optimized container image. So the answer to the question is, can we have an Ubuntu container that's small like Alpine and with 0 vulnerability count of known vulnerabilities? The answer is yes. In fact, we can have our cake and eat it too. So what we have now is an Ubuntu based image with no known vulnerabilities of comparable size to the slimmed Alpine image, but with none of the potential complexity and friction that comes with working with Alpine. It's also worth noting that there's a high risk vulnerability, which is CVE 2021-3999, that exists in glibc, and that vulnerability remains in the images based on Distroless and the official Python images, because they're both derived from Debian 11. Unlike Ubuntu, where that vulnerability has already been mitigated, and unlike Alpine, where that vulnerability never existed by virtue of Alpine using Muscle. So the whole idea that Distroless is meant to provide you with a greater degree of security because it has fewer packages is kind of torpedoed, because the very central capability that you need, glibc, has high risk vulnerabilities in it, and you can't update beyond it. You can't work around it. So let's take a look at what we've learned. Follow container best practice. It will help set you up for success. Always run internet-facing apps and services via unprivileged user accounts. Nobody in this case. Pin your base images and use a stable base image, and then apply the updates on top of that. Be mindful of layer caching, introducing potentially insecure packages into your container images. Container scanning and analysis are essential to fully understand what's inside your container. Do not install recommended packages to help keep your container slim and secure. Linux vendors have security SLAs, so think about how that impacts your selection of base image. So assess your base image options and pick what is most suitable for your project. You can slim just about any kind of container image, including those based on Alpine and Distroless. And slimming significantly reduces the vulnerability and attack surface. And yeah, that does look like more than 5, and you're welcome. So Yannick says, what people lie to us to make us use their product. I'm not sure. I think you're referring there to Distroless. I'm not sure that anyone's lying about Distroless. I think it's the assumptions people make that Distroless is small, therefore it must be more secure. I don't know that I've read anything on the Distroless project that actually says this is more secure. But it's an interesting exercise going through this process to actually, find out what the security posture of these most popular techniques are. So, thank you very much for listening. I hope you picked up a few tips to help improve the security of your containers. I invite you to give the Slim SaaS a try and the Docker extension. Both are free to use. And also take DockerSlim for a spin if you haven't done already. And if you have any questions, then you can join the Slim.AI Discord. I've put a rather fancy QR code on the screen there you can scan, or you can just head to the URL above my head and find the links to all of the places that we exist, including our Discord and our Twitter. And if you prefer to use Twitter, you can ask any questions of us there. So that's the end of the sort of presentation itself. But I just wanted to show you something else that I didn't get into in this presentation here. And it's about slimming and how you can kind of ignore all of this. So let's actually contradict everything and look at how you can use DockerSlim to sidestep a lot of this stuff. I think I'll use a terminal for this. So I have I've done it again. Wrong virtual screen. I have a bunch of images that I prepared earlier. It's just like Blue Peter. Here's some I made earlier. And what I want to focus on is this one here. So this is an Ubuntu based image where I prepared that image without removing the recommended packages. So consequently, I have an Ubuntu image that has my app inside it, and it's 431 megabytes, which is significantly bigger than the one here where I adhered to best practice, didn't install the recommended packages, and I have 300 megabytes smaller is that. So the vulnerability count here is obviously significantly more, but check this out. The jammy fat slim, I realize that's a bit of oxymoron. So this is the slimmed version from that fat container, is 25.5 megabytes. And look here, the jammy slim container is also 25.5 megabytes. So you can pour a massive container in that doesn't adhere to best practice, that maybe has terrible layer construction. You probably want to sort that out for build optimization reasons, but the result is identical. And what we can do is we can actually demonstrate that these are, in fact, the content of these two containers is the same. So let's go back to our Docker desktop extension. I'm struggling to see it in my screen here. There we go. So let's do this. I've done it again. I have to come down here. Right. So let's take our, what is it we're going to compare? The Slim we're going to compare with the Fat Slim. So there we go. We're going to take a look at these two side by side. Now there will be some sort of differences because there'll be things like timestamps and the bytecode and things like that may differ in some places. So if we actually look at the modifications, I think what we'll find is if I flatten this, maybe that will help. Yeah, it's the bytecode. So these are clearly going to be different because they were built at different times. And the cache, of course, the LD library cache is going to be slightly different as well. But other than that, you know, the stuff that you can't help but be different because of the time that they were built at different times, the actual content of these is the same. If we look here, they're only very slightly different sizes, and again, it's down to bytecode and caches. And we can see here, you know, they're very, very close in size, and link counts are very similar. So it looks like there's two differences, in fact. I might have to go and trace those down out of curiosity, but I'm almost going to bet that they're in the cache. So there you go. You can actually sidestep a lot of this, go straight to slimming your big, massive containers and get the same outcome of starting with, you know, a sort of a well-crafted container that adheres to best practice. So I just wanted to share that because I thought that that was, you know, fascinating that you can, when we talk about reducing friction for developers, this is one of the things that I'm referring to. You know, you don't have to go through that whole process of container best practice. It definitely helps if you do, because it will help with your deployment pipeline and what have you. But you can get the same outcome regardless. Go to the file tree. Oh, hang on. So my colleague is suggesting I do something. Oops, I've done that thing again. So sorry. Let's just bring this up. Go to the file tree and tick additions, and you will get what is different. Okay, so let's go to here. Go to the file system diff and choose the additions. Here we go. It is this symlinks. Okay, symlinks. So there we go, a couple of symlinks. I wonder why those symlinks are in one and not the other. I can't say, but there we go. Ostensibly the same. I just thought that was an interesting little little comparison at the end there. So there it is. That was the walkthrough. I've gone into it in a little bit more detail. Does that before we put a bow on it? Does anyone have any questions or comments about any of that haven't cropped up already? If not, that's fine. So this is kind of a very holistic view to sort of, container best practice, security best practice, and optimization techniques, and how all of that can work together in your best interests. Okay, well, thanks Yannick. Thank you for stopping by. It's lovely to see you again, by the way. I know we've been like ships passing in the night for several months, so you and I must have a catch up at some point. I look forward to finding out what's new with you. Thank you very much to all of you that stopped by. If there's anything from this, if you're watching this after the fact on YouTube, do head to our Discord and ask questions there if you've got follow-on questions. If any of you take a look at all of this after the fact, what I'll do is I'll post the presentation in the Discord after this live stream, and the presentation is not just the slides, it's all of the speaking notes as well. So it's like all of the content, including links to all of the tools and the studies and everything that backs up all of this. So I'll post that in the Discord after this, and you can take a look at some of this. And I'll also in the Discord post a link to where you can access all of the Docker files and the sample app and some convenient scripts that will build and automatically minify and run security analysis of everything. So you can, with one command, build those 30 odd containers and optimize them, and then you'll have all of the results locally that you can poke around and play with. So all of that will be in our Discord after this. It'll take me a few minutes to post it. But I don't see any more questions, so I'll assume we're done there. So thank you very much for everyone that stopped by. Thanks for the questions and the feedback, everyone. And I look forward to speaking to you in the next one, which will be the same time next week. And I can't remember what the topic might be. It might be something Raspberry Pi related. It might not be Raspberry Pi related, but it might be. So there we go. Thanks very much for coming, everyone, and we'll see you soon. Bye bye for now.